I first want to thank the local hosts for hosting us, inviting us. It is my first time to India, and as Olivier said, when he invited me to lecture here, I said on the condition that I get lots of paneer, and you guys have not failed at that. You guys are terrific, and thank you for being such a lovely host, and I'm excited about for the excursion today. Let's see. Also, I'd like to thank all the students here, all of you for being here, because it's been a long week. We still have another day or so, and I think this is going to be a lot of fun. Importantly, it's an informal lecture. Ask me questions. There's going to be a lot of BSM, a lot of things you haven't seen, a lot of things you have seen. If you've seen it all, that's even better. If something is not making sense and you just think I'm completely crazy, you're probably right, and just say, hey, Richard, I don't understand that. That's fine. I might not either, but we can talk about it. Let's see. Encourage us, just interrupt me. Just say, hey, Richard, just yell. I'm sorry if I don't hear you immediately, because it actually is loud up here. Okay, so this is the lectures I'm presenting today and tomorrow are on Introduction to Neutrino BSM and Neutrino Physics at Colliders, which is a very fun topic and something close and near and dear to my heart. These lectures are summer school style, unsurprisingly that we're at a school. So they're fast and intense. There's going to be a lot of material in a short amount of time. I'm going to try to go through things step by step, but there will be some jumping around. That being said, there also is way too much material in these slides, and that's kind of by construction. I don't expect to actually hit all the topics here. My goal is to get about 3/4 of the way through the slides, and Olivier will stop me when necessary. Let's see. This is not a historical talk. There are not as many references as should be. Read the papers, ask me later for some historical context. Additionally, so all of this is just preliminary, saying what this talk is and what it is not. This talk includes a lot of modern topics, a lot of modern research topics. And so it's often not everything, and a lot of the stuff you see here is not in textbooks. And because of that, one of the goals is to kind of fill in the gaps between coursework and research. As an example, a lot of what I'm going to show you, I've never seen myself in a lecture, only in either from research or by asking for derivations or doing them myself. Again, questions are welcome, and I'm sorry for the typo. The plan, like I said just a minute ago, is in 2 steps. The first step today is introduce you to neutrino oscillations, a whole big issue of neutrino masses. Why are neutrino masses a problem with the Standard Model, and why this is evidence for new physics? It's a strong statement, but it's really cool. So today is kind of just introduction to neutrino physics, neutrino, and the possible origins of neutrino masses. Tomorrow's lecture is bringing back to the collider focus, saying how can you test what I'm discussing today at colliders, and this is where we're going to see a lot of fun stuff, and it's a case study showing everything that we've seen this past week come to fruition. There's a lunch break at around 1, so Olivier will stop me, and trust me, I'm hungry already, so I'm not going to try to delay us. Okay. I'm going to give you the conclusion now in 1 slide, because if you just walk out of the lecture hall now because it's such a terrible talk, I don't blame you, but at least stay for this slide. The whole big picture is if you put all the fermion masses, elementary fermion masses, onto a single plot, you see the quark sector here, the charged lepton sector here, you see an electroweak sector here, MeV, and then you see, this is something that we've measured and known for a while. The electron's a half an MeV, the top is around 173 GeV, and then there's this desert, and neutrinos are here at the sub-eV scale. The fact that neutrinos are on this plot is why I'm standing here talking to you guys right now. The fact that neutrinos are on this plot is evidence of new physics, and there's unambiguous evidence that neutrinos have non-zero masses. I'm going to go through some of the examples and how we as a community understand this and accept this. The existence of neutrino masses is contrary to Standard Model particle physics, and under general arguments further means that there are new particles at hand. Investigating non-zero neutrino masses is a very active research field. I just kind of had a fun little inspired search last night. If you do HEP, pH, and neutrino and just ask in the past 5 years, in the title you get a little more than 5,000 hits altogether. Well, 2.5 for HEP pH, 1.1 for HEP X, so this is just from the past 4 or 5 years. Moreover, collider and oscillation facilities are complementary probes of neutrino physics. I don't like calling oscillation experiments neutrino experiments because you can do neutrino physics at the LHC and other fixed target experiments. But okay, neutrino oscillations. So let's go to Fermilab. Like I said, it's not a historical talk, so I'm already building up a neutrino beam. So what is a neutrino beam? I take a nice big energetic proton beam, you know, something like the LINAC or the main injector at Fermilab. Well, I haven't said. Right. Take the main injector at Fermilab, zip around all these high energy protons, and hit a fixed target. You know, if I have a bunch of protons hitting copper or something heavy, I'm going to make a bunch of pions. And so, you know, I have a nice little fancy magnet that collimates all the pions. Pions, pi pluses, pi minuses, they're going to decay dominantly to muons and nu mu's. And so if I can collimate the pion beam, when these decay along the beam line, I now have a nice rich beam of nu mu's and anti-nu mu's. And that's great. I have a nice little near detector where I measure the number of incoming neutrinos, and that's great. That's an good old-fashioned DIS experiment, a fixed target experiment. Now, if you have a little fun and you have a nice little research budget, you can actually point the entire apparatus into the ground. So you have your near detector just below ground, and then you put another detector on the other side of the Earth, say a far side like a home stake or something, and then you see how many nu mu events you have there. And then you compare how many nu mu's you had at the near detector and how many nu mu's you had in the far detector, and you realize that you have fewer than anticipated. Sure, there are some matter effects. You know, you are going through the Earth. The Earth will shield some neutrinos a bit, but by and large, you can estimate given how many initial neutrinos I have, how many final neutrinos I should have. And what you see is that there's a deficit. And this whole deficit is going along, is what we now call as, we associate this phenomenon with the neutrino oscillations. And so what's going on is that you make protons here, hit a fixed target, make pions. The pions will decay to nu mu's. You shoot this through the Earth, and then you have a near detector, far detector. And if you had no oscillations, you would have this standard prediction, and then you see a dip. So you don't have as many nu mu's in the second detector, in the far detector, as you do in the initial detector. So this deficit disappearance of anticipated nu mu's, or alternatively, what you do see is an appearance, an enhancement of the nu e's. You know, there are some pions decaying to electrons and nu e's, so you do expect to see some electron-flavored neutrinos, but you see more than anticipated. And this is now interpreted as starting off in one flavor eigenstate, namely the nu mu's, transitioning to a mass eigenstate. This is what propagates, and then on the other side you see in the second detector you see a second flavor. This is now known as neutrino flavor transitions or oscillations, and as an example of data being able to measure this, you have the NOVA experiment. So then the big question is, how does data describe this? And this is what I'm getting into, the neutrino oscillations, and namely the massive neutrino hypothesis. Right, so how do I describe a Lagrangian with massive neutrinos? Let's just start off with good old-fashioned gauge theory. So I have a left-handed doublet in a gauge eigenbasis, and then I just do almost a trivial or a tautological rotation to the flavor basis. If I expand my covariant derivative as we've done or should have done in QFT, you have the charge current interaction. So that's wow, that's g over square root of s. That should be g over square root of 2. You can tell that I do a lot of color calculations. So that's a weak coupling. That should be a square root of 2. Charge current, you're summing over all the different flavor eigenstates. You have a neutrino and a charged lepton, the left-handed chiral projection operator, and that's the Lagrangian in the standard model that describes neutrinos coupling to charged leptons and the W boson. If I have massive neutrinos, then I can decompose both my charged leptons and my neutrinos into their mass eigenbases by just doing a linear superposition or a unitary transformation, if you will. So I'm just going to rotate my, my neutrinos in the flavor basis into their mass eigenstates, and so that's just some unitary transformation. Same with the charged leptons into their mass eigenbases. So this is what you would see it be half an MeV, 100 MeV, or 1.7 GeV for the tau. Then I just plug this expression into here, this expression into here, and then I have this double sum, and I just do this implicit sum. And now this is a Lagrangian that's describing how massive neutrinos of a particular mass eigenstate is coupling to charged leptons of a different mass eigenstate. You see that really the difference between this Lagrangian and that expression is this mixing factor, which means my Feynman rules are just modified by what's called the PM&S mixing factor. So it's just like the CKM, or if I make the CKM diagonal and I turn off quark mixing, I don't have any of the mixing factors in my Feynman rules. But here I've turned on neutrino mixing, I've turned on neutrino masses, which allows me to do this rotation, and I just pick up a small little mixing factor. Right, okay, so this is how I can describe in scattering interactions massive neutrinos coupling to the rest of the standard model currents. I can do the same for Z's and under certain assumptions. I can do this with Higgs, but that's a strong assumption. Am I going too fast? Raise your hand if you think I'm going fine. Okay, wow, okay, very good. I'm probably still gonna, well, okay, right, so now let's forget taus exist. Let's forget two generations exist. I'm just gonna suppose that we have two generations here. So we have an electron, a neutrino, a muon neutrino, and we have two mass eigenstates. Let's just suppose this and forget anything else about the universe. If I just have a 2x2 system, then decomposing my flavor basis into mass basis is just that one little mixing angle decomposition. So then I can just explicitly describe one state vector as a linear superposition of the two mass eigenstates, and I'm just going to say that mu1 is a light mass eigenstate and mu2 is a heavy mass eigenstate. And so there you just see cosine and sine if you want to do it explicitly. If you treat neutrino propagation over a distance in space-time as a plane wave, then you're going to be able to pick up an evolution factor U. And so then the way you describe a neutrino state propagating through space-time from A to B is just given by this sum up definition statement. So you have the mu eigenstate in a particular flavor propagating from A to B, and well, then that's given by a evolution factor acting on the state vector, which then I decompose into the light mass eigenstate, the heavy mass eigenstate, and you see I have a factor. So the next couple of slides I'm going to talk about this evolution factor, what it is, and how to actually give you an explicit, drive an explicit expression. So if I'm doing the plane wave, then I just make the simple assumption that my direction of propagation is the same distance of which I'm considering. So if I'm talking about a neutrino going from A to B, this is also the direction of its momentum. So if I'm making that assumption, then you see that this evolution factor is just this wave, this usual phase expression with a forward momentum acting on the position vector. And then I just decompose this into my energy and my momentum and distance, 3 momentum and 3 distance. And then while under this assumption of the direction of neutrino is along the direction I'm looking at, then I can just write this as L. So that's going to be the different distance. Right, now let's go to the ultra-relativistic limit, because there have been a lot of tests looking for neutrino masses before. For example, beta decay. You know very well the mass of a neutron and or an atomic isotope. You look for the final state proton or the final state isotope. You measure the electron's energy very well, and this sets by energy conservation, a constraint on the neutrino mass, and this is small. So already we know that we're dealing with light neutrino masses. If I then shove a 50 GeV proton beam behind me, such that I'm making a 10 to 50 GeV neutrino, and I know that the neutrino mass is under an EV, is under 10 EV just from neutrino beta decay, or I'm sorry, not neutrino double beta decay, just regular honest to goodness beta decay, then I know I'm in the ultra-relativistic limit. So if I'm in the ultra-relativistic limit, where masses are very, very small compared to the energy, then I can say that this energy and momentum factor, I can kind of just pull out the distance, because the difference between a small little mass, a particle with a small little mass propagating and a massless particle propagating, this time difference over a length of L is going to be small. So I can just pull out the L, and then I just complete the numerator, complete the square. So I'm now taking the difference over the sum, and the ultra-relativistic limit is saying that the two is essentially the same. Here, this is an exact result giving me the mass squared over the energy. So this is the origin of m squared over E in the neutrino oscillation fact, in neutrino oscillations. You're taking the ultra-relativistic limit. Right, since the masses are small compared to the energies, as I was saying, then we can just say that the energies contained by the two are going to be the same. Now, if you have the decays of two particles, of two pions going to neutrinos, if the neutrinos have different masses, then you're going to have different momentum shifts between the two, and let's just say that by and large they have the same mass. And so that we can use the same evolution factor. So explicitly, the space-time evolution vectors for the electrons and muons, neutrinos are given by this the PM and S mixing factor, so just a sine or cosine. This plane wave factor, and the light mass eigenstate, heavy mass eigenstate state vectors. So all of this just to get this, but now we can actually compute scattering amplitudes, transition amplitudes. If I had a third mass eigenstate, I just do the same. I just have another term here. If I had a hypothetical fourth or fifth or sixth mass eigenstate, you can just see that I would just continue this on and extend UE2 to UE3 to UE4. And this is just saying what's the likelihood of finding an electron in mass eigenstate 2. Right, so if I want to compute oscillation transitions and I have state vectors, then in order to compute, say, the survival rate to have a nu mu remain a nu mu, then the matrix element amplitude is just going to be the inner product of the final state. That should be a nu mu. Shoot, sorry. That should be a nu mu. Oh, yeah, sorry. That's a nu mu acting on nu mu. And then I decompose the nu mu on the nu mu. Oh, dear. What did I do? Yeah, sorry. I changed this at the last minute. So these should be nu mu's. I feel embarrassed. Right, okay. So there's the evolution factor. So we quite literally just took this expression here, plugged it in here, and this is the conjugate. So this. And then you just kind of propagate it through. So the light mass eigenstates are going to operate on each other because they're mass eigenstates, and so different mass eigenstates are going to be orthogonal to each other, and the light mass eigenstates are going to give you 1. And so then if you just simplify, you get UE1, yeah. Yeah. Well, I'm hesitant to say that this is mu. So hold on. Oh, I feel embarrassed. Is it, yeah, well, okay, well, let's continue on this because maybe the typo's here. Right, if I then square this, because it looks like I started off with nu mu, but I wrote down for nu e, so let's just continue the computation. So I have the mass eigenstates, so these expressions are going to be for U to E transition. And if I do, yeah, I know what I did, because I was changing it, because I had, so yesterday I had the mu to E transition, and then I thought, well, let's also have the mu to mu transition. And I didn't propagate everything through the slides, so I apologize for that. So these are the expressions for mu to E transition. So nu mu to nu E transition. So if we want to reproduce the neutrino muon deficit, let's just consider either the mu to mu or mu to E transition. And then the matrix element is just going to be given by the inner product, in which we're decomposing the flavor states into the light and heavy mass eigenstates, and the transition into the time-evolved light mass eigenstate and the time-evolved heavy mass eigenstates. The orthogonality of mass eigenstates holds nonetheless, regardless of what basis. And for the nu mu to nu E transition, I have this phase factor with this orthogonality, with the non-vanishing state vectors. I can then calculate the probability by just squaring the amplitude. So the nu mu to nu E transition is going to be the nu mu to nu E amplitude squared, and that's going to give me this term squared, that term squared, the interference, and the interference between the two. So here you actually now start seeing the emergence of the differences of mass squareds of delta 2, 1. And so this is defined as to m2 squared minus m1 squared. So now I have the correct formula for nu mu to nu mu. So that's correct, because that's going to be 1 minus something. So this should be nu E, that should be nu E, that should be nu E. If you have the correct formula, and do it, I leave this as an exercise for everyone. It's brilliant, isn't it? Right, so let's just recall that, you know, it's a 2 to 2 rotation, so we just have a sine and cosine here. So the UE1, U mu 2 are cosine. So these are the diagonal terms, and these are the off-diagonal terms giving you a sine. The nu mu to nu mu expression is this precisely after a little bit of algebra, which if you do a little more algebra, you get 1 minus this product. Quite simple. It's quite remarkable that just a 1-to-1 system will give you, well, actually it's a 1 plus 1 system. It's not so difficult. If you start adding a 3 to 3, the expressions become much larger because you also have complex phases. 3 plus 1 is quite lengthy, but at that point you no longer need to write analytic formula, just have a Mathematica or C++ code, or Fortran if you will. But this is quite interesting because I think there's a lot to unpack here. So here's we're talking about the probability of starting off with a nu mu and ending up with a nu mu after propagating through a distance of L. So we start with the first term, and this is pretty much saying you have unitarity. You know, if I didn't have neutrino masses, that would vanish. If I didn't have any neutrino mixing, that would vanish. And that would say that the likelihood of my neutrinos staying in the same flavor eigenstate is 1. But now you actually start seeing something cool, because if I'm starting to plot this as a function of distance propagated, or as a function of energy, which often it's plotted as length over energy in order to compare different experiments, you start seeing that there's not just oscillatory behavior, but different beats, where this would give you the minimum of the dip, and this would give you the spacing between the beats. By conservation probability, the mu to mu survival and the mu to E disappearance rate are going to add up to 1. So that means we can write down the mu to nu E appearance probability as this. So it's going to be 1 minus the survival rate, and it's just this factor here. So again, that would tell us that the maximum of the peak, and this would give the spacing of the beats. A little more explicitly, here we have just a kind of a toy computation, of which here is the probability as a function of L over E. And you see that the maximum of the nu E appearance is given by this sine 2 theta squared, and this is going to correspond to the minimum of the dip. And the separation between the valleys and the troughs are given by this the spacing. In particular, if you can factor out the L over E, is giving you a measurement of delta delta 2 1 squared. So, right. that's neutrino oscillations in a heartbeat. You know, the success and maturity of the neutrino oscillation paradigm provides us with an amazing probe of new physics. You know, first, you know, you can ask, are there additional neutrinos? Because I just showed you a two-state system. Obviously, there are three neutrinos. How would this impact things? If we were to have additional stereo neutrinos, this would manifest as non-unitarity of the 3x3 BSM matrix. Now, you can also ask, well, once we start getting to 3 generations or more, there is now a possibility to pick up CP phases. Is there CP violation in the lepton sector? Other fun little questions to ask is, what is driving the CKM matrix to be diagonal, but yet still have a large CP violation, CKM to be diagonal, but the PM&S matrix to be off diagonal? And by that I mean, if you look at the elements, the different mixing factors, they're all large, and you don't have a hierarchy like you do for the CKM matrix. Another question is, are neutrinos Majorana? There we go. So I was wondering what happened to that plot. So here again, I'm just showing you this plot we had earlier today, showing you the number of events as a function of reconstructed neutrino energy, and you see that you kind of see this dip. So this would be nu mu to nu mu, and you just see you start up high and that it disappears. A big question of active research right now is whether or not neutrinos are Majorana. All the fermions we've seen in the standard model are Dirac, except after electroweak symmetry breaking, neutrinos are singlet in both QCD and QED, and therefore they're allowed to be their own antiparticle. And if they are their own antiparticle, this would mean that there's a breaking of lepton number conservation, B minus L, and it would be measurable. And so also, it's quite a remarkable question about whether or not they're Majorana. What I kind of want to focus the rest of the talk is, what is the origin of neutrino masses? Because now showing that, you know, if neutrinos have masses, you're able to derive such oscillation phenomena, and you see that this oscillation phenomena is occurring, this is establishing that neutrinos have mass. Okay, neutrinos have mass, so what? Is this a big issue? And this is what brings me to the massive neutrino problem. So, okay, neutrinos have masses. They have masses that are sub-eV, and again, everything was on putting all the fermion masses onto the scale. You see neutrinos have masses much smaller than the charged lepton, the charged fermion sector. The reason why this is an issue is that the standard model doesn't explain neutrino masses. There are no right-handed neutrinos. If I wanted to generate a Dirac mass for neutrinos like I do for the electron or for the top quark, I would need a right-handed neutrino. And then I can just write down this Euclid coupling with the charged lepton doublet with the lepton SU2 doublet acting on the Higgs with this right-handed neutrino to select out the neutrino mass. This would then generate through the Higgs vev a nice little Dirac mass term, and this could in principle explain neutrino masses. Except that there is no evidence for, there has been no sign of right-handed neutrino. And if you go through literature, you see that, you know, in Weinberg's model of leptons, right-handed neutrinos are not proposed. As we've established to date, there are no right-handed neutrinos as defined in the standard model. And so this is the significance of neutrino oscillations, because neutrino masses have now demonstrated that the Lagrangian of the universe is not well described by just the standard model Lagrangian. Instead, the universe is well described by the standard model Lagrangian and neutrino masses. And this is the origin of the statement that neutrino masses is evidence for new physics, and that neutrino masses implies the existence of beyond the standard model physics. Another way of putting this is a little more, it's a more advanced statement, it's a more nuanced way of putting things. But Ernest Ma in 98 has a nice little paper kind of outlining the different ways of generating neutrino masses in a renormalizable manner. And it kind of goes like this. So the strong statement is that non-zero neutrino masses implies that new particles exist. So how can we make such a strong statement? You know, we know that neutrino masses are non-zero, as I just tried to convey to you. But we also know that they participate in left-handed currents. Again, if you go to the old if you go to the old beta decay experiments, you can have a polarized nucleus, you see the polarization of electron by angular momentum arguments, and knowing that W's are left-handed currents, you establish that neutrinos are left-handed in beta decay. So we know that neutrinos are massive and they participate in left-handed currents. If I wanted to write neutrinos in a renormalizable manner, a neutrino mass in a renormalizable manner, knowing this, then I either have to write down a left-handed Majorana neutrino mass. In other words, saying that not only do I have L mu, but I'm also pairing it with its conjugate, which this is only allowed if left-handed neutrinos are Majorana, then I can write down this left-handed Majorana mass. Alternatively, if I hypothesize a right-handed neutrino, then I can generate the Dirac mass. And this is how I would generate a dimension 4 mass term for neutrinos that is renormalizable. We've spent a lot of money on building the LHC. We've discovered and established that not only the Higgs boson exists, but also the Higgs mechanism is really at play in generating heavy fermion masses. Then if I think about this carefully, this is violating gauge invariance because you're talking about trying to generate a neutrino mass from an operator that does not conserve SU2 quantum numbers. Similar here, I think this is a little more striking in which you see something with weak isospin. This is a singlet, and this field operator would not conserve weak isospin or weak hypercharge. So that means I'm going to have to promote the Dirac mass or left-handed Majorana mass to a field Svet. And for the Dirac mass, this can be simply done by the standard model Higgs, but if I had a left-handed Majorana mass, then this would have to introduce a new field to generate this Svet. And so here it is. The statement is, if neutrino masses are non-zero, and I like renormalizability, and renormalizability does work. This is what's been guiding us in Hadron Collider physics and QCD for the past several decades. So I want to keep it, and this is something that we see in the standard model. I also like gauge invariance. It's a very strong statement to say that I need gauge invariance, but again, the standard model does work, and we've seen through the discovery of the Higgs that gauge invariance is a guiding principle. If I require both renormalizability and gauge invariance, then that means I must have some new particle to explain neutrino mass, which is quite remarkable if you think about it, because we've started off with some small sub-dinky sub-eV object, observable, and from that we gather that there are new particles. But then, the question is, what are these particles? What's the identity of these particles? They might be charged under some new gauge symmetry or old gauge symmetry. For example, this is a scalar that would be charged under the electroweak group, or it could be a singlet. This singlet in the standard model might contain new quantum numbers. It might be charged under a new gauge group, for example, U1b minus L. And it's quite exciting because from there are a lot of different options. And what we do know, however, is that these particles must couple to the Higgs and or couple to the Higgs and charged leptons, which often induces a lepton number violation and charged lepton flare violation. In other words, the non-conservation of lepton number through a process and the non-conservation of flavor through a number. How am I on time? 20 minutes. Beautiful. Right. Okay. So pathways to naturally small neutrino masses. So in 10 minutes, I'm going to cover. I'll get to 10 slides. Is that 20 minutes in total or 20 minutes including questions?
Not including questions.
Not including questions. Oh, great. I can actually do this. Right. You can tell I was trying to burn through oscillations despite the typos, which I apologize again for. Right, because I want to get here. So, because this is where we start getting to the more BSM, because neutrino mass is already BSM, but this is where we're starting to get into more modern research. So again, as I said earlier, the spinor gauge algebra plus renormalizability restriction really restricts ways to build up neutrino masses in a renormalizable gauge invariant manner. And if you want to do this minimally, and by minimally I mean what is the minimal number of degrees of freedom you need to generate neutrino masses, and by degrees of freedom a multiplet that obey standard model principles, there are 3 or 4 types depending on how you want to count. The type 0 is that I just introduce a right-handed neutrino and a tiny Yukawa coupling. In other words, do this and make this 10 to the minus 12. If that's the electroweak scale, if that's 246 GeV divided by root 2, then in principle, this is possible. But in order to do this, I have a singlet fermion. A right-handed neutrino has no color quantum numbers, it has no weak quantum numbers, it has no hypercharged quantum numbers. It's a singlet, and therefore I'm not forbidden to write down a Majorana mass for it. But that would break lepton number, which is an accidental symmetry in the Standard model. And fine, I can do this, but then I have to impose a new symmetry of the Standard model and say that the Standard model obeys lepton number conservation. So if I want to invoke this route, I have to propose a new symmetry for the Standard model, which is a large, heavy statement. So it's possible, but tiny Yukawa couplings for neutrinos is also theoretically unsatisfying. Why are all the other fermions so much heavier than neutrinos? So it's swapping out one problem with another problem. I can do the type 1 seesaw, which I'll explain in a bit, so I'm just kind of giving you a quick survey of the different seesaw mechanisms, kind of the basic tenets, and then I'll go into them in a little more detail. I can introduce a right-handed neutrino, keep the Majorana mass term. So again, I have this Dirac mass, but then I introduce a Majorana mass that I've not forbidden. If I go to one scale, then I can have a neutrino mass that goes like 1 over the Majorana mass scale, and voila. If this is heavy and that's small, then I'm not able to mix into the mass eigenstate, and so this is suppressing things. There's another variant of there's another seesaw mechanism called the type 2 seesaw mechanism, in which instead of hypothesizing the existence of a right-handed neutrino or any new fermion, you instead hypothesize the existence of a scalar triplet. So it's a scalar multiplet of SU2. The neat thing is that you don't need a right-handed neutrino. So whenever someone says neutrino masses implies that a right-handed neutrino exists, that is untrue, because I can generate neutrino masses with a left-handed Majorana mass. So essentially this. So if that acquires a VEV, I get that, which is a qualitatively different chiral structure, coupling structure than for a Dirac neutrino. And then I just have this lepton doublet acting on this triplet scalar, acting on another lepton doublet, put everything on this VEV. Again, I can get a neutrino mass that's proportional to a tiny VEV. The type 3 seesaw does a little mixture of both, in which I have a fermion triplet. So I have a fermion that's in a 3 representation of SU2. I just do a little bit of group algebra. The mechanism follows similar to type 1. So think of type 3 as a mixture of type 1 and type 2. There are less minimal models, and when I say less minimal models, I don't mean that in a pejorative fashion. I actually mean that in an exciting fashion, because there's no statement, there's no theory statement that only one of these is the correct answer. If I start looking into GUTs, grand unified theories, gate extended models, or realistic models of, say, baryogenesis, it's easy to start getting field content that I can trigger a 1 plus 2 or 2 plus 3 or 1 plus 3 or 1 plus 2 plus 3 seesaw mechanism, hybrid seesaw mechanism. You also have caveats to statements, because this is just, if you try to do mass diagonalization, it's just 1 plus 1. So there are flavor models you can impose. There's also loop level models you can do, and all of this is way too much for a 1-hour lecture. Already what I'm showing you is more than enough for a 1-hour lecture. But I continue. So type 1 seesaw, and type 1 seesaws at colliders. So in the canonical seesaw, type 1 seesaw, as I was saying earlier, I just extend the standard model with the right-handed neutrino. And so the Lagrangian would be the standard model plus the kinetic term for right-handed neutrino. I have the Dirac mass, and I have a Majorana mass. And here I'm just going to assume a 1 plus 1 generation scenario. I like keeping things simple, even though life is much more complicated, and this is going to bite me in about 20 seconds. So if I expand all of the SE2 indices and get the Dirac mass from here and have the Majorana mass and put this into a nice mass mixing matrix, I have the left-handed neutrino, the conjugate of the right, and this mass matrix, you see the Dirac masses here and the Majorana mass here. So really, this is just these two lines just kind of rewritten in a slightly different group structure. Right, now let's make what's called the seesaw assumption, the usual seesaw hypothesis, in which I say that I hypothesize that the Majorana mass scale is much, much larger than the Dirac mass scale. If I then try to diagonalize this mass matrix, I find out that I get a one mass eigenstate that goes like the Dirac mass times this suppression factor, where the suppression factor is md over mu r. And they also find the second mass eigenstate, which goes like the heavy neutrino, the Majorana mass scale. And so this is historically what has been called the seesaw mechanism, although the language then does not match up with the language now. Today's seesaw mechanism describes a variety of mechanisms, encompasses a variety of mechanisms to explain just how neutrinos can obtain small masses. And so here you see very clearly that if I have a very large Majorana mass, then I get very small, vanishingly small light mass eigenstates for neutrinos. The trick here, the caveat here that I have to make is that this is just a 1+1 scenario. Realistic models have to describe at least two mass eigenstates, because if you look at oscillation data, we have evidence for at least two non-zero mass eigenstates. The third one might have a mass as well, but as we saw earlier, you're only sensitive to the differences of the masses squared. So we know at least two light neutrinos have masses, maybe three, but when you take that into account, this is not a simple 2 by 2 matrix. This is going to be a 4 by 4 or 6 by 6 matrix, and you see that this is a much larger, but you then have a very rich flavor structure. The important thing is that the mixing goes not like MD over MR, but goes like this matrix multiplication. And this naive idea that if you have a large, because you're dealing with a matrix structure here, you can't always guarantee that this Majorana mass is going to be large compared to the Dirac mass. In fact, you can invert it and go to a different limit. I'll get to that in a second, but the point I want to make here at this moment is that you're kind of seeing seesaw mechanisms at work already. So we introduced a new fermion, we wrote down the most general Lagrangian, we combined the Dirac mass terms to be able to write a mass matrix, and made a hypothesis about the scale of new physics. Here we said that the scale of new physics is much, much larger than the lecture week scale, and then we found a way of suppressing the light mass eigenstates. And so this is sort of the way the seesaw mechanisms are working, is that you're establishing neutrino masses through Euclid couplings of some kind, either to the standard model Higgs itself or to a new scalar potential. And these new scalar sectors are requiring vacuum excitation values and generating masses for the light neutrino masses. Either way, you're getting a suppressed effective neutrino mass through mixing, either through mixing of the standard model neutrinos with the new states you're hypothesizing, or through the Higgs sectors I'll show you in a second. However, another thing I would like to emphasize at this point is that seesaws are more frameworks than models. And by this I mean I just showed you a nice little 1+1 way of generating tiny neutrino masses, and the simplicity of this mechanism means I can embed it in 4 theories, more realistic theories. Now there's a subtle difference between a seesaw mechanism, such as here, and a seesaw model. A seesaw model is a full theory that can reproduce data. It might have only 3 new degrees of freedom, but the full seesaw model would have to describe data. And if you go beyond just a singlet, this actually kind of makes life kind of fun, because you have the other seesaw types that I described. You can also invoke seesaw mechanisms in the MSSM, in extra dimension models, and particularly in grand unified theories. Going back to the flavor issue, if I have a realistic model in a type 1 scenario, I have this huge mixing structure. I have theoretic neutrinos, 3 stellar neutrinos, I have that matrix, so this is one flavor plus one sterile. If I have 3 active neutrinos and 3 sterile neutrinos, this is going to be a 6x6 matrix. This is massive. And I don't want to go anywhere near that. But the nice thing about it being massive is that you can play a lot of flavor games. And what you see is that in a pure type 1 scenario in which you only have singular neutrinos, beautiful, tiny neutrino masses can be obtained in 2 ways. This is a language we're trying to establish in the literature, is that you can have a high-scale seesaw, in which a high-scale seesaw, the Majorana mass is going to be much, much larger than Dirac mass. In that case, as I showed you just a few slides ago, you typically get that the light neutrino masses go like 1 over the Majorana mass scale. You have alternatively what are called in the literature, and you see this on the archive all the time, you even see this on the archive this morning, what are called low-scale seesaws. And these are the situations in which you make the inverted hypothesis of the Majorana mass being much, much smaller than the electron weak scale. And when you work out the mass eigenvalues there, you see that the light neutrino mass actually is proportional to this lepton number violating scale. So in this situation, what happens is when you turn off the lepton number violation, this is also turning off the mass eigenstate of the light neutrino. So we actually don't know where new physics is, because the lepton number violation can be, the source of new physics can be low scale or can be at high scale. If it's at high scale, we can do things like EFTs, as we saw earlier today. If it's low scale, then we can do direct experiments. But at the end of the day, if you want to, we don't need to worry about that. At the end of the day, you can just make an agnostic hypothesis and say, let's just look for these things. And if, I've already given you the Feynman rules for describing a heavy neutrino coupling to the 2 standard model currents. Just to go back to refresh you guys, you people. Here we go. So here I was able to show you how to get a Feynman rule for coupling a massive neutrino to a charged lepton. If I had more sterile neutrinos, I would just extend this summation to include the heavy mass eigenstates, the additional sterile neutrinos, and then I would have another mixing element here that describes TeV scale neutrino, for example, coupling to charged leptons and the standard model. So again, all you have to do is modify the Feynman rule with the new mixing parameter. And this allows me then to couple 2 standard model currents through mixing. And so I can do heavy neutrinos produced from charge currents through the Higgs, through vector boson fusion. And if I go through all the calculations, as a lot of us have been doing the past couple years, we see cross-section plots. So here I'm showing cross-sections for heavy neutrino production as a function of heavy neutrino mass. And you see things for normalized to the mixing. And you see at the LHC the dominance of this charge current production. So you said 10 minutes? Oh, okay, fine, yeah. So you see that this W charge current production of the heavy neutrino is dominant, and then you get vector boson fusion. If you go to 100 TeV collider, you see that gluon fusion starts taking over, and then vector boson fusion takes over. So across collider energies and masses, you see this huge, fantastic interplay between PDFs and matrix elements. Right, so again, this is kind of just giving you a survey now of what's going on. You do have searches for this at the LHC, and you do have, and other fixed target experiments, and you do have limits on this mixing, and you do have sensitivity to the future colliders, which is kind of cool, because that means the LHC can compete with dedicated experiments for charged lepton flavor violation. In the last 5 minutes, I'm just going to show you a brief little picture of the type 2 seesaw. Type 3 seesaw follows, but I'm pretty much on time to finish when Olivia gives me the okay to stop. Again, just another example of how you can do neutrino masses without having a right-handed neutrino. For example, you can have a scalar multiplet that's a triplet under SU2. So it's in the 3 representation, and you assign it lepton number -2. And so you have a neutral fellow that acquires a VEV, you have a singly charge, and because it's a triplet, so that means it has a +1 isospin, 0, and -1 isospin, and a hypercharge of +1, so that's 1 + 1. That'll give you a doubly charged scalar, which is really cool, because then you can make a doubly charged Higgs or doubly charged scalars at the LHC. What's important is that if you look at the scalar potential, the delta is mixing with the standard model Higgs, you have this mass mixing term. Again, this is where it's always coming back to some new particle mixing with standard model particles. Here, instead of a fermion mixing with standard model neutrinos, or in the type 3, new fermions mixing with the charged leptons, you have here a new scalar mixing with the standard model Higgs. And so this term right here, if the scalars carry lepton number -2, this term explicitly breaks lepton number and will induce a VEV for this delta, a new vacuum expectation value. And this, again, factors of 2. 2's and S's apparently look the same for me. The delta, the vacuum expectation value of this delta is going to be proportional to this lepton number violating scale. So again, if I turn off the VEV, or alternatively turn off the lepton number violation, then neutrinos go massless. And then if I build up the neutrino masses, I just have the lepton doublet here, delta, another lepton doublet, and I just work out the quick little algebra, and I see left-handed Majorana neutrino masses. So again, generating light neutrino masses without invoking right-handed neutrino. Some new cross-section plots, old cross-section plots by other people exist, but these are latest and greatest numbers. And so you see associated production. So a doubly charged particle with a singly charged Higgs is the dominant production mechanism. You have a photon-photon fusion. Fabio, ignore that. But again, you see at 100 TeV that the cross sections are quite large. Again, this is active searches. There are active searches for this at the LHC. CMS and Atlas are both looking for doubly charged Higgs production decaying to electrons and muons, and the limits are at about a TeV, much like for heavy neutrinos. Type 3 Seesaw, I won't go through it, but again, there are production rates, and you can see as a function of collider energy, things go up quite large. Searches for this as well. The reason why I'm flashing all of these searches is also to kind of give you an idea of what I'm going to talk about tomorrow. In addition, I want to emphasize that these are active research topics, that CMS and Atlas are actively trying to discover these things. So at this point, I'm pretty much done, because this is where I begin the next lecture. So with that, I want to say thank you for your time, and please ask me questions.
Any questions? Yes.
Slide 11.
Yes. Just before that, I believe. Just before that, the flavor to mass relationship.
Sorry, 10.
I think yes.
There's a lot here. I gave everyone a lot. More earlier?
Yeah, before I think. So it's fine. So the e to the power L divided by 2e. So
Here.
the L you took same in the as the coefficient of this V1, nu1 and nu2, right? So can't we change that L to some L1 and L2?
Yeah.
I believe that, I mean, I am not sure, but...
Well, for here, it's going to be the same L because my experiments are the same location. So I have the same initial detector for both, and I have the same far detector for both. And so the L would be the same. The question is whether or not the time propagation is the same. Or if you want another way of putting it, is the energy going to be the same? So I can either fix energy or I can fix the distance.
Any other questions?
So the recent oscillation data, if I'm not wrong, favor the sterile neutrino paradigm. Does it mean that's a problem for type 2 Seesaw models?
Say the first part one more time. I want to be clear about this. Say the first part of your question one more time.
I'm not an expert on it, so it's maybe very naive, but I have the impression that the recent oscillation data is favoring the presence of a sterile neutrino, which are there in the type 1, but not there in the type 2.
By that, I'm picking on you because you're a senior faculty. Do you mean global fits or global fits? So global fits describe the three neutrino paradigm. By global fits, I mean there are many oscillation experiments. You have atmospheric neutrinos, so essentially just a giant water tank, and you look at neutrinos going through here. You have accelerator facilities. You have IceCube, which is in its own class. These, by and large, favor that there are only 3 light mass eigenstates. There are recent results at Fermilab with the mini boon suggesting that there might be a sterile neutrino. However, there's a difference between having an excess and the interpretation. They have an excess in a small little in a region of their data, and to parameterize this excess of data, they've assumed a 1 flavor plus 1 sterile neutrino hypothesis, essentially the 1 plus 1 mixing scenario I showed here and derived for you guys. This is how the data has been parameterized, but that does not mean that it is a sterile neutrino, because if you then take this data and try to see how good a fit you can get with having just a 3 sterile, 3 plus 1 sterile, or 3 active plus 1 sterile, or just 3 active, the 3 active and no sterile is a better fit. There are new ideas which came out in the archive just the past couple weeks, saying, well, what if there are sterile neutrinos but they're decaying? But these are latest and greatest topics, and I can't really comment on that because these are ideas that need to be fleshed out. But presently, the oscillation data favors only 3 light mass eigenstates. That does not mean that there are more mass eigenstates, it's just that they would be at a much higher mass, because you see, for example, here, if the mass splitting is, maybe you can't see it explicitly here. If the mass splitting is above the beam energy, you're not going to have a neutrino that's able to propagate into this higher mass eigenstate. If the neutrino beam is 10 GeV, but the mass eigenstate is at 50 GeV, there's no way this neutrino will be able to propagate into that heavy mass eigenstate by energy conservation.
When we only consider the new me to new E as like this picture, and just consider the mixing with 2 times 2 matrix, how large is the theta is? For example, sine square 2 theta is mixing angle?
Theta is the mixing angle. Theta is the mixing angle where it's the same theta here.
Thank you very much.
Yeah.
How large is this mixing angle to realize the oscillation to new me to new E?
I was looking at this earlier. The theta 1, 2 is about, this is about 45, 48 degrees. So it's large. It's a large mixing angle. I always mix up theta 1, 2 because I much prefer to think in terms of because these are physically observable and you extract the mixing, but one of the angles is about 45 degrees and the other is about 30 degrees, and because of their similarities, 2 nice geometric shapes that we grew up with, there's a lot of, I don't want to say numerology, but there's a lot of flavor hypotheses suggesting, oh, well, this must be, or this could be explained by simple geometric arguments. So suppose it's you have 2 mixing angles, so you have you can build up a triangle, and if one's 45 degrees, one's 30 degrees, and then you can satisfy nice geometric properties, or it's suggestive that if you have some geometrically inspired flavor model, can reproduce this. However, these also usually hypothesize that a theta 1,3, so the mixing between electron flavor and tau is 0, but this is about 8 degrees, so it's far from 0.
Oh, thank you very much.
So the constraints which you put on the masses, those are all disappearance experiments or?
At the LHC?
Yeah.
These are direct searches.
So how do you do that?
So you're producing them, say, through pair production, and these are decayed to electrons each. So, for example, you can have a quark-quark annihilation through a neutral current into a pair of W-charged hits. You know, this part is more for tomorrow, but I'm still just flashing them just to kind of give you a survey. But these doubly charged scalars can then decay into pairs of electrons, for example. So you assume that the branching fraction, the branching rate to electrons is 30%, or to muons is 30%, and so you have two scalars that are each going to 2 electrons and 2 muons, and then you look for anomalous production of these.
But the question is, each one will act as a background for the remainings, right? Because
Sorry, I didn't quite hear that.
see, all these diagrams, some of them will act as a background for the other one. So, how do you take care of it?
So
You put an upper limit on it, right? By considering only one diagram and only the standard model things.
So, no, I understand. I'm just trying to think of the issue. So you shouldn't think of these additional diagrams as being the background for the process. If you neglect them in your simulation, they're still occurring, but that would, but unless it's going to be of the same order as the process itself, you typically neglect it. But I think what's a great example, in this Atlas search, they included both the neutral current and the charge current. And so these are two different processes that occur on the same order, and so they didn't treat these other diagrams as background, they consider them only as signal. But instead of simulating all of the signal processes, they made the approximation to only consider the dominant two signal processes, namely the neutral current and the charge current production. And you see that these are the dominant production mechanisms, and so those are the ones you want to keep. And so the Atlas search here included both of those. So one should not think of the other diagrams as background. One should think that the signal process is only approximating the full signal of the inclusive production.
Okay, I think we can thank Seesaw and all the speakers this morning.